Okay, so I'm going to take us through some basic portions of the notes on vertical and horizontal asymptotes for rational functions. So the first thing we need to remember is that a rational function is undefined when the denominator equals 0. So what we need to do is set the denominator equal to 0 and solve for any values of x in the denominator that would break the function or make the denominator 0 and therefore the function undefined. So when you're going to graph that, the next question, when you're going to graph that, it's going to graph like an asymptote. So you could have one vertical asymptote, you could have two vertical asymptotes, you could have lots of vertical asymptotes, but anytime the function is undefined, you're going to get an asymptote graphically. All right, so we're going to write the equations of the vertical asymptotes, and then we're going to sketch them. So all we have to do here is set the denominator equal to 0, x equals -2 is my asymptote. There will be a singular vertical asymptote at x equals -2. This second one, if we could factor the top, we would want to factor that to see if we could cancel anything out. That would give us wholes. But in this case, the top is not factorable. So we just want to set the denominator equal to 0. And then zero product property tells us there are two ways this can happen. Either 3x plus 2 equals 0 or x minus 1 equals 0. We want to solve for both. X equals -2/3. Or x equals 1. So this is going to have two vertical asymptotes, one at +1 and one at -2/3. Vertical asymptotes aren't the only kind of discontinuity. We also have wholes. So we are looking for not only vertical asymptotes, but wholes. So we're going to factor the top. Top is a difference of two squares. So it factors into x plus 5 times x minus 5. The bottom, we can just factor out an x, and that gives us x minus 5. Now, because we have an x minus 5 in the numerator and an x minus 5 in the denominator, we can cancel those out. That means that at x equals 5, we have a whole, or a value that's going to make this original function would be undefined if we plug in the value of 5. However, because it cancels out, that means it's a whole and not an asymptote. The value that does not cancel out is x, so x equals 0 is a vertical asymptote. So at x equals 0, we have a vertical asymptote, and at x equals 5, you'll have a whole wherever that part of the function is. So assuming the function looks something like this, there's going to be a whole at the value x equals 5, an undefined location on this graph. Okay, same idea for the next one. We want to factor both the numerator and the denominator. What multiplies to 6 and adds to 7 is going to be 1 and 6. So that gives us x plus 1 over 3 and x plus 6 over 3. 6 over 3 simplifies. 1 over 3 does not, so that's where our 3 comes out. So we get 3x plus 1. And x plus 2, that's my new numerator. What multiplies to 4 and adds to 4 is 2 and 2. So my new denominator is x plus 2 times x plus 2. Again, one of these is going to cancel out. So that would be a whole. However, if you notice, this is also x plus 2. And because it's still there, it's going to be an asymptote. So at -2, we're going to have an vertical asymptote. And because the function will not graph there at all, we aren't going to have a whole, even though these two canceled out. If this value were anything other than -2 to break that function, then we would also have a whole. But in this case, we don't. We have an asymptote, which sort of overrides the whole. All right. End behavior is going to be based on the horizontal asymptotes, and horizontal asymptotes come from Bobo Botten eats DC. So let's really quickly review that down here. Bobo stands for bigger on bottom. The horizontal asymptote will be y equals 0. So bigger on bottom, y equals 0 is the acronym for Bobo here. This is referring to the exponent values. So an example of this would be like x over x squared. Well, the exponent on the bottom is 2 and the exponent on the top is 1. Therefore, this is bigger on the bottom, and the horizontal asymptote would be at y equals 0 for that rational function. Then we have button, bigger on top, no horizontal asymptote. So bigger on top, no horizontal asymptote. And lastly, eats DC, which stands for exponents are the same, divide the coefficients. And these are the leading coefficients attached to that degree or the highest exponent value for your function. All right, so in this example here, this is a bigger on bottom because we have a 3 on the bottom and a 2 on the top. So bigger on bottom, y equals 0. So this has a horizontal asymptote at y equals 0. That means as x goes to negative infinity, y is going to approach 0. And as x goes to infinity, y is also going to approach 0. And for this class, you don't need to know if we're rising or falling. You'll get into that in pre-calc next year. All right, in our next example, we have the same exponent value. We have squared on the top and the bottom. So this is eats DC. Exponents are the same. We're going to divide the coefficients. The first coefficient is 3. The second one is 1. So we're going to take 3 and divide by 1, which gives us 3. So this has a horizontal asymptote at y equals 3, which means as x goes to negative infinity, y is approaching 3. And as x goes to positive infinity, y is still approaching 3 because it's going to approach those horizontal asymptotes. All right, this is bigger on the top. So we have 3 as the exponent on top, 2 as the exponent on the bottom. This means there is no horizontal asymptote. So this one you're going to want to investigate a little bit. But as x goes to negative infinity, y is going to go somewhere, not toward an asymptote because there isn't one. So it's either going to go up or down. And as x goes to infinity, same thing. So if you do a quick graph of this in Desmos, you'll be able to see what's happening here. So if we were to divide x cubed by x to the power of 2, and you're going to see this basically just creates a linear function. So because these are positive, both values are positive, our linear function is just going to be increasing as we go from left to right. So our y value as we go to negative infinity is also going to negative infinity, and our y value as we go to positive infinity is also going to positive infinity. Again, it's not truly linear, but it simplifies to be linear in nature, so that dictates our end behavior for our rational function when we don't have horizontal asymptotes. All right, we are looking for all of the asymptotes and or holes. We're supposed to state the domain and describe the end behavior for these last two. So in order to find holes and or vertical asymptotes, you're going to factor both of these things. To find the horizontal asymptotes and therefore the end behavior, you're looking at Bobo Button eats DC. And lastly, the domain is going to be everything except holes or asymptotes, and the range is going to be everything except horizontal asymptotes, and you're going to use the horizontal asymptotes for the end behavior. I will make a key for these last two problems so that you have access to all of this information.